Welcome! In this session, we'll explore the problem titled Rabbits in Forest. This is a fascinating question that challenges us to think critically about group behaviors and apply mathematical reasoning to find an optimal solution. Let's dive in and solve this step by step. In this problem, you are in a forest with many rabbits, and some of them provide a hint about how many other rabbits share the same color as them. Your task is to determine the minimum number of rabbits that could be in the forest based on this information. The input to the problem is an array called answers, where each element represents the answer given by a rabbit. For example, if a rabbit answers X, it means there are X plus 1 rabbits of the same color, including itself. The output is a single integer representing the minimum number of rabbits in the forest. The key challenge here is to use the rabbits' answers to group them efficiently and minimize the total number of rabbits while still satisfying all the given answers. Let's explore this concept further with an example. Suppose the input is answers equals 1, 1, 2, dot. The first two rabbits both say 1, which means each of them belongs to a group of 2 rabbits of the same color. These 2 rabbits can belong to the same group since their answers align with this grouping. The third rabbit says 2, meaning it belongs to a group of 3 rabbits of the same color. Combining these groups, we get 2 rabbits from the first group and 3 from the second, giving a total of 5 rabbits. This is the minimum number of rabbits that satisfies the given answers. Now, consider another example where answers equals 10, 10, 10, dot. Here, each rabbit answers 10, which means each one belongs to a group of 11 rabbits of the same color, including itself. Since all 3 rabbits provide the same answer, they can be grouped together. This means we only need one group of 11 rabbits to satisfy all 3 answers. Therefore, the total minimum number of rabbits in this case is 11. In the next example, the input is an empty array, answers equals, dot. When there are no rabbits present, there are no answers to process. Consequently, the minimum number of rabbits in the forest is 0. This example highlights the edge case where the input array is empty, and the output is straightforward. Finally, let's consider some additional edge cases. For instance, when all rabbits answer 0, it implies that each rabbit is unique and does not share its color with any other rabbit. In this case, the minimum number of rabbits is simply the length of the answers array. On the other hand, when there are repeating answers, such as multiple rabbits giving the same number, we must group them efficiently to minimize the total count. For large numbers in the input, it's important that the solution handles these scenarios correctly by grouping rabbits without exceeding the constraints. These considerations ensure that the solution is both accurate and optimized for all possible inputs. When approaching the rabbits in forest problem, the central task is to determine the minimum number of rabbits that could exist based on the answers they provide. Each rabbit specifies how many others of the same color exist, and from this information, we infer group sizes and calculate the total number of rabbits. One possible way to tackle this is through a brute force approach. The intuition here is to simulate every possible grouping of rabbits based on their answers. By doing this, we ensure that each rabbit is either added to an existing group or a new group is created to accommodate it. The steps involve parsing the input list of answers, then using a greedy strategy to allocate rabbits into appropriate groups. Finally, we sum up the group sizes to get the total number of rabbits. However, while this method is straightforward, it comes with significant trade-offs. The time complexity is n squared, as each rabbit might require multiple checks to determine its group allocation, and the space complexity is n for storing group information. This approach, while intuitive, is computationally expensive and unsuitable for larger inputs due to its inefficiency. A more efficient solution leverages an optimized approach using a hash map. The insight here is that if a rabbit says there are X other rabbits of the same color, they collectively form a group of size X plus 1. Rabbits with the same answer can share a group, but only up to this group size. If the number of such rabbits exceeds X plus 1, additional groups are required. To implement this, we first count the frequency of each answer using a hash map. Next, for each unique answer X, we calculate the number of groups needed as the ceiling of the frequency divided by X plus 1. Multiplying this number of groups by the group size gives the total rabbits for that answer. By summing up these totals across all answers, we arrive at the minimum number of rabbits. This approach is both time and space efficient, with a time complexity of O(n), since we process each answer only once, and a space complexity of O(n) for the hash map. Compared to the brute force method, this solution eliminates unnecessary overhead and scales well with larger inputs, making it a practical choice. For this problem, we selected the optimized approach using a hash map due to its balance of efficiency and simplicity. The key realization that drives this strategy is that a rabbit's answer x defines a group size of x plus 1. Rabbits with the same answer can share a group, but only up to this limit. If the number of rabbits with the same answer exceeds the group size, additional groups must be formed. These observations allow us to avoid simulating group allocations explicitly. Instead, we focus on counting the frequencies of answers and calculating the required group sizes directly. This insight reduces the problem to a straightforward calculation, making it both time efficient and easy to implement. By focusing on these mathematical properties, we're able to solve the problem effectively while minimizing computational overhead. Comparing the two approaches highlights why the optimized solution is the better choice. While the brute force method is conceptually simpler, it is highly inefficient with a time complexity of O(n squared, making it impractical for larger inputs. In contrast, the hash map-based solution runs in O(n) time and is also space efficient, making it ideal for handling large-scale inputs. The optimized approach avoids the unnecessary complexity of explicitly managing group allocations by directly leveraging the mathematical relationships in the problem. This balance between clarity and efficiency makes it the preferred strategy for solving the rabbits in forest problem, as it ensures both accuracy and scalability. To solve this problem, we first need to break it down into clear steps. The problem asks us to calculate the minimum number of rabbits in the forest based on the responses they provide. Each rabbit's answer tells us how many other rabbits of the same color exist. For example, if a rabbit says 3, it implies there are 4 rabbits in total, including itself, of that color. These answers are provided as a list of integers, and our task is to determine the smallest possible total number of rabbits. To do this, we start by grouping the responses by their values. Using a dictionary, we can organize the data so that each unique answer becomes a key, and the value is the count of rabbits that gave that answer. For instance, if the input list is 1, 1, 2, 2, 2, 3, the resulting dictionary would be 1, 2, 2, 3, 3, 1. This structure is critical as it allows us to efficiently process each unique answer. Once grouped, we calculate the group sizes. For a given answer x, the group size is x plus 1, since the rabbit itself is included. We then determine how many groups are needed by dividing the count of rabbits for that answer by the group size and applying the ceiling function. This ensures we account for any remaining rabbits that don't completely fill a group. Finally, we calculate the total rabbits for that answer by multiplying the number of groups by the group size. This ensures we capture all the rabbits implied by that particular answer, even if some groups aren't fully filled. After calculating the rabbits for each unique answer, the next step is to sum up these totals to get the minimum number of rabbits in the forest. By iterating over the answers in the dictionary, we maintain a running sum that aggregates the rabbits for all groups. This running total will represent our final result. Additionally, it's important to handle edge cases to ensure the solution is robust. For example, if the input list is empty, there are no rabbits in the forest, and the output should simply be 0. Another case to consider is when all rabbits give the same answer, which means multiple groups of the same size may exist, and we need to calculate this correctly. We must also account for scenarios where a single rabbit gives a very large number as its answer. In such cases, the algorithm should still handle the calculation efficiently without unnecessary complexity. The key insight here is that while rabbits with the same answer can be grouped together, their total count cannot exceed the group size implied by their answer. This ensures that the solution respects the constraints of the problem. By using a dictionary for grouping and mathematical calculations for deriving group sizes, we avoid the need for manually simulating the placement of rabbits, which significantly optimizes performance. The use of the ceiling function is also critical for handling cases where the count of rabbits doesn't neatly divide into full groups, ensuring that every rabbit is accounted for. To implement this solution effectively, we rely on specific data structures and operations. The dictionary is the core data structure, as it allows us to group rabbits by their answers efficiently. This enables quick lookups and reduces the need to repeatedly iterate over the input list, which would be computationally expensive. Additionally, we use mathematical functions like the ceiling function to handle cases where the count of rabbits is not evenly divisible by the group size. This ensures that we account for all rabbits, even when they form partial groups. The key operations in this algorithm include grouping the rabbits by their answers, calculating the group sizes, and summing up the total rabbits. Grouping the responses has a time complexity of O, n, where n is the length of the input list. Calculating the group sizes involves iterating over the unique answers, which has a time complexity of O, k, where k is the number of unique answers. Since k is always less than or equal to n, the overall complexity remains O, n. Finally, summing up the rabbits for all unique answers is another O, k operation, making the entire algorithm highly efficient. The final algorithm is optimized for both clarity and performance. It leverages mathematical calculations to avoid unnecessary simulation and handles edge cases gracefully, ensuring the solution is both accurate and efficient for any valid input. This Python implementation solves the LeetCode problem number 781, rabbits in forest, by calculating the minimum number of rabbits in the forest based on their answers. Explanation. 1. Input parsing and counter creation. The input answers is a list of integers, where each integer represents how many other rabbits of the same color a rabbit claims exist. We use counter from the collections module to count the frequency of each unique answer. This helps us group rabbits based on their claims. 2. Iterating over answers. For each unique answer and its count in the counter. Calculate group _size as answer plus 1 because a rabbit claiming X implies a group of X plus 1 rabbits, including itself. Determine the number of such groups needed using count plus group _size 1 / group _size. This formula performs a ceiling division to ensure we handle cases where the count doesn't perfectly divide into groups. 3. Summing rabbit counts. Multiply the number of groups by group _size to calculate the total rabbits for that answer. Add this value to total _rabbits. 4. Return result. After processing all unique answers, total _rabbits holds the minimum number of rabbits in the forest, which is returned as the result. Example. For an input like 1, 1, 2, the counter gives 1, 2, 2, 1. For answer equals 1 with count equals 2, group _size is 2. Only one group is needed, contributing 2 rabbits. For answer equals 2 with count equals 1, group _size is 3. One group is needed, contributing 3 rabbits. The total is 2 plus 3 equals 5 rabbits. Complexity. Time complexity, O, n, where n is the length of answers, as we iterate through the list in counts. Space complexity, O, k, where k is the number of unique answers, due to the counter. This solution efficiently handles both large and small inputs while ensuring correctness. This is the Java implementation of the rabbits in forest problem, mirroring the logic of the provided Python solution. Key differences include using Java's hashmap for counting occurrences and explicit type declarations. The logic for grouping rabbits based on their answers and calculating the minimum number of rabbits remains the same, with adjustments for Java's syntax. To solve this problem, we start by analyzing the input array 1, 1, 2. The first step is to count how many times each answer appears using Python's counter. This gives us a frequency count of counter 1, 2, 2, 1, meaning the answer 1 appears twice and 2 appears once. Next, we process each unique answer in the frequency dictionary. Let's begin with the answer 1, which has a count of 2. The group size for this answer is calculated as answer plus 1, which equals 2. Since we have 2 rabbits reporting this answer, we calculate the number of groups as count plus group _size 1 / group _size. Here, this evaluates to 2 plus 2 to 1 / 2, which equals 1 group. Each group contributes group _size rabbits, so we add 1 * 2 equals 2 rabbits to the total. At this point, the total number of rabbits is 2. Next, we process the answer 2, which has a count of 1. Using the same logic, the group size is answer plus 1, which equals 3. For one rabbit reporting this answer, the number of groups is calculated as count plus group underscore size 1 / group underscore size. Substituting the values, this becomes 1 plus 3 to 1 / 3, which equals 1 group. Each group contributes group underscore size rabbits, so we add 1 asterisk 3 equals 3 rabbits to the total. Adding this to our previous total, we now have 2 plus 3 equals 5 rabbits. This gives us the final output for this example, which is 5 total rabbits. Now, let's consider a different input, 10, 10, 10. We start again by counting the frequency of each answer, which results in counter 10, 3. This tells us that the answer 10 appears 3 times. Next, we process this unique answer. For 10, the group size is answer plus 1, which equals 11. With 3 rabbits reporting this answer, we calculate the number of groups as count plus group underscore size 1 / group underscore size. Substituting the values, this becomes 3 plus 11 to 1 / 11, which simplifies to 1 group. Each group contributes group underscore size rabbits, so we add 1 asterisk 11 equals 11 rabbits to the total. Since there are no other answers to process, the total number of rabbits for this input is 11. Now consider the input 0, 0, 1, 1, 1. First, we count the frequencies of each answer, resulting in counter 1, 3, 0, 2. This tells us that the answer 1 appears 3 times, and 0 appears twice. Let's start with the answer 0, which has a count of 2. The group size is answer plus 1, which equals 1. With 2 rabbits reporting this answer, the number of groups is calculated as count plus group underscore size 1 / group underscore size. Substituting the values, this becomes 2 plus 1 to 1 / 1, which evaluates to 2 groups. Each group contributes group underscore size rabbits, so we add 2 asterisk 1 equals 2 rabbits to the total. Now, moving to the answer 1, which has a count of 3, the group size is answer plus 1, which equals 2. With 3 rabbits reporting this answer, the number of groups is calculated as count plus group underscore size 1 / group underscore size, giving us 3 plus 2 to 1 / 2, which equals 2 groups. Each group contributes group underscore size rabbits, so we add 2 asterisk 2 equals 4 rabbits to the total. Adding these values together, the total is 2 plus 4 equals 6 rabbits. For this input, the computation is complete, and the final output is 6 total rabbits. This result accounts for all the groups formed based on the answers given, ensuring that we've accounted for every rabbit in the forest. Here, we start by analyzing the time complexity of the solution. The first step involves counting the frequency of each unique answer in the input list using the counter class from the collections module. This operation iterates through the entire answers list once, which means it runs in n time, where n is the length of the list. Next, we loop through the unique answers using the counts.items method. If there are k unique answers, this loop performs k iterations. Within each iteration, operations like calculating the group size, determining the number of groups, and updating the total count of rabbits are constant time operations, or O1. Therefore, the total time for this loop is k. Since k, the number of unique answers, is at most n in the worst-case scenario, where every answer is unique, this step also has a time complexity of n. Now, combining these steps, the time complexity of the solution is determined by the 2 main operations, the construction of the counter object, which is n, and the iteration over the unique answers, which is also n, in the worst case. Adding these together gives an overall time complexity of n. Shifting focus to space complexity, we begin with the counter object. This object stores the frequency of each unique answer, and its space usage is proportional to the number of unique answers, or k. Since k is bounded by n, the space requirement for the counter is n. Additionally, variables like group underscore size, groups, and total underscore rabbits consume a fixed amount of space, which is constant, or 1. To summarize the overall space complexity, the most significant factor is the memory used by the counter object, which is n. Therefore, the space complexity of the solution is n. Now, let's compare this optimized approach with a brute force method. In a naive approach, we might attempt to simulate all possible groups of rabbits directly, iterating over each answer and manually calculating group memberships. Such an approach would involve repeatedly processing overlapping groups, leading to a time complexity of O(n) superscript 2, or worse in the worst case. In contrast, the current solution leverages a hash map via the counter to consolidate counts, allowing us to compute results efficiently in a single pass. This improvement reduces the time complexity to O(n), making the solution significantly more efficient. When analyzing the algorithm's performance under different scenarios, we observe that the best case time complexity is still O(n). This is because the algorithm always needs to process the entire answers list and iterate over the unique counts, regardless of the input distribution. Similarly, the space complexity in the best case remains O(n), as the counter object depends on the unique answers. In the average case, the number of unique answers, k, will typically be smaller than n but still proportional to it. This results in average case time and space complexities of O(n). In the worst case, all answers are unique, meaning k equals n. Here, both the time and space complexities remain O(n). Thus, the algorithm maintains consistent performance characteristics across all scenarios. Finally, let's briefly review the mathematical proof for the time and space complexity. Constructing the frequency map using counter involves iterating through the input list, which takes O(n) time. Processing the map involves constant time operations for each unique answer, and since the number of unique answers is at most n, this step also takes O(n). Adding these together gives an overall time complexity of O(n) plus O(n), which simplifies to O(n). For space complexity, the dominant factor is the counter object, which requires storage proportional to the number of unique answers. In the worst case, where all answers are unique, this space requirement becomes O(n). Thus, the solution's space complexity is also O(n). When solving this problem, there are a few common mistakes to watch out for. First, it's easy to misinterpret the rabbit's answer. The number a rabbit gives represents the count of other rabbits of the same color, not including itself. This means the total group size is actually the reported answer plus 1. Misunderstanding this can lead to underestimating the total number of rabbits, particularly when multiple rabbits give the same answer. Another common issue is failing to properly group rabbits based on their answers. For example, if 2 rabbits say 2, they could either belong to the same group of 3 rabbits or to 2 separate groups. It's crucial to consider the context of their answers to group them correctly. Lastly, overcounting duplicate groups is another frequent error. If multiple rabbits give the same answer, some solutions mistakenly count the same group multiple times. To avoid this, you can use a dictionary to track and ensure that each group is only counted once. Now, let's consider additional pitfalls. Forgetting to handle edge cases is a major issue. For example, what happens if there's only one rabbit and it says 0? Or if all rabbits give the same answer? Your implementation should explicitly address these scenarios to be robust. Another mistake is inefficient sorting. Sorting the entire list of answers can unnecessarily increase the time complexity of your solution. Instead, you can optimize by grouping answers directly using a frequency map, which eliminates the need for sorting altogether. By handling edge cases carefully and avoiding redundant sorting, you'll make your solution both accurate and efficient. The key to solving this problem lies in grouping rabbits based on their answers. Each rabbit's answer defines the size of the group it belongs to, and it's important to understand that multiple groups of the same size can exist independently. To optimize your solution, you can use a hash map to count the frequency of each response. This approach avoids sorting and reduces the time complexity to O(n). When discussing this problem in interviews, it's helpful to clarify your understanding with examples. For instance, you might ask questions like, if all rabbits say 0, does that mean every rabbit is a unique color, or what if all rabbits give the same non-zero number? These clarifications ensure you're interpreting the problem correctly. Be prepared to discuss edge cases, such as when there's only one rabbit or when inputs are large with many repetitive responses. Finally, this problem is conceptually similar to other LeetCode problems like longest consecutive sequence, majority element, and top k frequent elements, which also involve grouping or frequency analysis. Drawing these parallels can help you approach the problem more effectively. There are several approaches you can take to solve this problem, each with its own trade-offs. The brute force approach involves manually grouping rabbits based on their responses. While this method is straightforward and may work for small inputs, it has a time complexity of n squared, making it impractical for larger datasets or interviews. A more efficient method is the hash map approach. Here, you use a frequency map to count how many rabbits give each response, and then compute the total by grouping them efficiently. This method achieves n time complexity, but it does require additional space to store the map. Another alternative is sorting-based grouping. By sorting the responses first, you can iterate through the list and group rabbits as you go. While this method simplifies the grouping process, the sorting step increases the time complexity to n log n. Overall, the hash map approach is usually the best choice for its balance between efficiency and clarity, especially in interview settings. Great job! To wrap up, we reviewed the key algorithm and its complexity, along with the major takeaways from the session. Problems like this highlight the power of mathematical reasoning and efficient data structures like hash maps. Thanks for tuning in. Be sure to like, share, and subscribe for more coding content. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!